I'm Bruce. I am an adjunct professor as of 5 years ago at Western. Was working in the oil industry down in Texas. I'm going to be talking to you about some work I've been doing on carbon, characterizing the Cambrian of Southern Ontario for carbon capture and storage. Independently, it's nice to see what Alan and Frank have been doing. We're looking at these things separately. We're bringing our expertise from different perspectives. It's fun to see things that we see in common and things that we see are different. So yeah, a bit of an introduction to me, a little bit about the carbon sequestration, what I've been seeing, things that need some work, and then wrap up. This has been known for at least 20 years. The Cambrian is the play. What I'm going to say is that to move forward, we need to start thinking like an explorationist in the petroleum system. There's a lot we don't know. We don't have the data. We got to start thinking about like an explorationist. And I don't have time to talk about all the things that I've been doing in the last 3.5 years or so. So I'm going to give you a sampler of some of the things that I've been doing. A little bit about me. PhD in the 1930s here at Western. Moved around from various places. The circle bit is, I think, going to give you a feel for the perspective that I'm bringing to this. For 12 years, I was working for major oil companies down in Houston. We're doing high-end exploration. Should we get into India? Should we get into Venezuela? Those types of things. Major development projects. How are we going to drill 100 wells when each one costs $10 million each? So big time. So you need to think about, I think about things from a very big perspective. My way of looking at this whole perspective, characterizing the subsurface, I came up with this name, carbon sequestration geosystems. Sometimes people call these things storage complexes. I think there's specific parts of the puzzle that you have to put together to really understand if a stratigraphic unit's got any perspective. What I would do, and this is, for me, this is a screening exercise. This is triage. You start looking at what data is available, what you need to know. Start off with setting the big broad scale tectonic setting. Think about the stratigraphy and sedimentology, because that helps you predict properties. Not because it's geologically fun, it's because it helps you predict properties that you need to know. And then you integrate these things to try and identify, do you have a suitable trap? And then you got to start thinking about geomechanical integrity. Are you going to start inducing seismicity those types of things? And as I say, screening phase, if I was working for ConocoPhillips or if I was working for Equinor, I might have 6 months, I might have a year to do this kind of stuff. And that's the perspective I brought to this. So first thing you would do is, what data is available? Is it available to you during screening? What's available? How good quality is it? And so on. And typically, as a big company, you like to work with seismic data. What you see is there's large areas of onshore that have no seismic data at all. A lot of times the seismic data is poor quality 2D seismic data. We didn't have information about what's going on in the offshore. There are a bunch of wells. As Alan and Maurice mentioned yesterday, a lot of them have really crappy log data sets from sort of a modern perspective. They're not sort of modern logging suites, right? And there have been some publications. Ideally, you'd like to be able to milk what's known and sort of build on that, but there's not a lot published. There's been work done, but there's not really a lot published on the Cambrian. So I've got to think of how to do things quickly. Here's why I'm saying you have to develop an exploration mindset. So here's the Niagara Peninsula. The yellow dots show Precambrian penetrations. The red lines show the seismic data that is available through the website. And what you see in an area that conceivably could have lots of potential for carbon capture and storage is there's no data. And even some of those wells that are on there are crappy. They don't have good modern logging suites or that type of stuff. So what do you do when you're working in areas of no data? You've got to think like an explorationist. How do you predict what you're going to find in these areas? And if you're a large company, what you start thinking about is, how were the sediments deposited? Can you predict geometries of sandstones? Can you predict geometries of reefs or whatever it is? And what's their structural setting? Are you likely to find faults? Are you likely to find fractures? Those things, you don't do them because you're a geologist and you think they're fun. You do them because they help you predict properties away from available data control. So you drill a well and nothing comes up. does that condemn the entire Niagara Peninsula? Or if you drilled 5 kilometers away, would you have been able to do something? Or you get really good results, are they going to last? If you drill 5, you establish another hub 10 kilometers away, will you get the same kind of success? That's exploration. You have to predict what you're going to find there, and you do it but through fundamental geology. So whipping through things quickly, broad-scale structural tectonic setting. People have been working on this kind of stuff for a long, long time. Mountain building events, stresses. When was this area stressed? When could fractures and faults and things have happened? And I won't go into all the details, but you start identifying when this area was squeezed, and conceivably you could have faults and fractures develop at those times. Faults. Latest available fault map that I know of is the one Terry put together back in 2010. You look at it, there's some straight line faults, which is the best you can do with available data, but that's not what real faults look like. Faults bend, they curve, they branch. And when you start looking at how you build a map, you can't put faults in where there's no data. It's that simple, right? So you know that this is the best quality fault map that you could do with the available data, but you know there's a lot that you're not going to be able to see. And as an example, I'll show you some stuff from another project I'm working on, a grad student and I are working on. This is something known as the Aquastore site in southeastern Saskatchewan. There's Alberta and Manitoba and the Canada-US border. These are the 1 to 250,000 faults that you can download from the government website. And you can see where the oil and gas activity is, can't you, right? Because there's a lot of seismic data down in here that allows you to map faults. So the Aquastore people decided they were going to put in their carbon capture and storage facility in through here. These are townships, so that's 6 miles by 6 miles. That's where they decided they're going to put the well. And you can see, well, you know, they drilled it far away from any existing faults, right? Or relatively, they had to put it on their property. They drilled it away from existing faults. Then they collected some 3D seismic data after they drilled the injector well. And when you start looking at the injector well and where the faults are, what you realize is they almost drilled straight into a normal fault. They missed it by about 100 meters. And what that has is a huge impact on the plume where the CO2 can go. You have to have 3D seismic data to really establish where faults are. There's no question about it. Strike slip faulting, I won't go through all this, but Trenton Black River, there's a bunch of diagnostic type faults that you see at the Trenton Black River that, again, when you look at where the data control is, it sets up these hydrothermal Dolomite things here. It sets up Albie and Scipio. There's hydrothermal Dolomites in Saybrook, and these are images from there. There's stuff in New York. There's no data there. Are there hydrothermal Dolomite systems there? Other fault systems? There's no data. The Cambrian stratigraphy, people have talked about what a mess this is. Me coming into a new basin where I look at this and say, okay, well, on one side, you got to call it one set of names. On another side, you got to call it another set of names. What I do from a basin screening perspective is say, I'm going to call it units 1, 2, 3, 4, 5. I'm not going to get lost up in sort of the terminology from a screening perspective. So I go off and start mapping. So this is the Cambrian section. This is kind of duplicates Bob Travail's map from a section from 1990. I see very similar geometries to him. This is the Cambrian section through here. The red bars show where there's core. I'm using a combination of gamma ray logs and neutron and density logs to identify lithology because you can't just use gamma ray. And so here's the yellow stuff is mostly sand with some dolomite. The blue stuff's mostly dolomite with some sand. Gray stuff's kind of a mix. So I've got this stratigraphic framework. I use digital logs. I don't use paper copies of things. I use digital logs. And when you do that and you use I've got a nice software suite at Western, you start doing the 3D model building, you start doing the kind of visualization. So here's like you're standing in northwestern New York, looking up towards London, somewhere in here. You're standing on the Precambrian surface, you're looking up at the Trenton, the base of the Queenston, and so on. Here's the stratigraphic geometries I show on that one cross section. Use 3D visualization to make sure you're not messing up your interpretations and to give you a good gut feeling of what's going on. So here's the thickness of the Cambrian. This has all been done before. There's nothing new. But if you think about a quick triage kind of perspective, where's the Cambrian deeper than 800 meters? Where's the Cambrian present? And you do the overlap of those things. and what you find is the fairway that you focus on. And that's really simple. One of the things that has been missing up until now is the mineralogy of these things. There's descriptions of sandy Dolomites and Dolomitic sandstones and things. So from the core back there, we've got 16 different XRD measurements. The blue stuff is dolomite, the yellow stuff is quartz, the orange are different types of potassium feldspar. You can see there's some sandstones that's a dolomitic sandstone. You can see places where over half the rock is potassium feldspar. There's some of the sandstones have more potassium feldspar, some of it's less. It's a real dog's breakfast full of kind of things. And one of the ways where that bites you is when you're doing petrophysics. So this is a multi-min plot. It's mineralogy based on the logs as presented by the vendor from 2012 analyses. And here's a gamma ray log over here. This is supposed to be shale. This is supposed to be sand. This is supposed to be calcite or limestone. This is supposed to be dolomite. When you plot the XRD measurements on there, you realize it's absolute garbage. They hadn't calibrated the petrophysics to XRD measurements. That's stuff that I would see all the time in the big companies. You have to do that stuff in these complex units. Otherwise, your petrophysical measurements are going to go south, and they're going to go south really quickly. So moving forward, if you're going to be doing this, if you're going to be working in the Cambrian, get XRD to calibrate the petrophysics. Comparing Cambrian here to other places, what I've done is I've taken porosity measurements from south of the border where the Mount Simon's being used for carbon capture and storage, and then some porosity permeability measurements from the Aquastor site. And the colored things are porosity permeability measurements from some of the Cambrian wells from the Basal sandstone that you could call Potsdam or Mount Simon. This looks really good from a perspective of carbon capture and storage, comparing what we've got here to other places. SEM. This is something that I convinced NRCan that needed to be done. Sooner or later, 4 or 5 years from now, if somebody's injecting CO2 into these things, the fluids are going to interact with the rocks, and you have to know what's down there. These are not tanks. Sometimes you see people think about this as a big sand tank. It's very heterogeneous. And when you start looking at the core back there, what I see are a whole bunch of different types of sedimentary structures that allow me to identify how those things were deposited, what types of environments they were deposited in. So there's burrows, there's stromatolites, there's carbonate hard grounds and things. And what that allows me to say is that all this stuff was deposited in a shallow marine environment. When I think of a shallow marine environment, I think of something that's continuous along shore and discontinuous and a perpendicular to the shore. So hypothetically, if we were to drill a well here, if this is the Mount Simon down and through here, we should be able to predict that properties will be continuous in kind of a northeast-southwest direction over distances of hundreds of meters to kilometers. Things might change more rapidly in that direction. It's all very qualitative. I can't give you decimal places, but it's not like I don't know anything. So you put together the depositional environment, it allows you to make some qualitative predictions. Something that came up as I was doing this work is the fluids in the pore spaces. People talk about this as being a saline aquifer, and if you've got a saline aquifer, the CO2 rises to the surface. Well, there's a lot of shows in here. There's places where you got oil. The pore spaces have got hydrocarbons in them, which means a lot of different things. One of them means that the pore fluids are going to be compressible, so the pressure pulse doesn't extend out as quickly as you might think it might, or as far as you might think it might. You can do some log analysis where there's logs available, and they're not available everywhere. But the pore filling fluids are going to have a big impact on how this thing, how pressures transmit in it, but also on how the injected CO2 will work. So here's the picture I'm coming up with. This is the ideal situation. You're injecting CO2 into a nice homogeneous tank that's full of brine. You inject CO2 and it rises to the surface. We know that's not the case. There's layers, there's bedding, different properties, different porosity and permeabilities. So if you inject, it's going to go laterally. It's going to be constrained to the sort of higher permeability layers. It's not going to go up. Things are going to go laterally, which can be a very good thing. But then, instead of having brine like blue, I've got a tan color to say that you've got some sort of mix of hydrocarbons in fluids. And under some circumstances, this injected CO2 can be denser than the ambient fluids, and it's sink. What do we know about the in situ fluids? Nothing. So is that going to happen? I don't know, but it's something you need to know. You need to think about. So the reservoir, to me, is going to be some combination of that and that. It's going to be one complicated mess. And what do you do in that case? You try it. Simple traps, we've got 500 meters of tight as a thick limestone and impermeable shales. Traps not going to be a big thing. Are there faults that could compromise the integrity of the seal? Well, we're back to this kind of system here where we don't have data in a lot of places, right? So maybe you kind of predict when would certain faults have formed in response to certain erodies. Can you make some gut feeling kind of predictions? Structural analysis, hazard mapping, inducing seismicity, characterizing boreholes for drilling and that kind of stuff, geomechanics. To really establish geomechanical stability, there's some things you need. You need elastic properties. You need to be able to predict what Young's modulus is and Poisson's ratio and so on from the reservoir and the cap rocks. You need in situ pressure measurements and stress measurements. You need maps of ambient seismicity. Where are the faults? Are there earthquakes? Those types of things. You need fault maps. What I can tell you is right now, there's none of this stuff publicly available. This stuff is few and far between, and the fault maps are definitely not modern quality, especially in places where there's no data. There's a lot of work that needs to be done in this space, data that needs to be collected, analyses that need to be done. Ambient seismicity, well, this is a map of the earthquakes from 1973 to 2023 from the GSE's websites. I superimposed that on the first derivative of the Aeromag data. You know, can you see anything? Well, I grew up in Hamilton. There's a lot of earthquakes there, but I never felt them, so they're low magnitude. There's some stuff down here near Windsor, and sorry, a whole bunch of stuff here near Toledo. But when you put the faults on, well, and there's our fairway. Lots of this area, including this area down here, there's not a lot of ambient seismicity there. That's probably a good thing. It's probably telling you there's not a critically stressed faults in there. And what it means is if you start seeing seismicity in these areas, you're probably the one that's inducing it by changing the stress regime with pore filling fluids. Something else that has come out is natural fractures up the yin-yang in this stuff. There's things that we call deformation bands in the sandstones. Discrete natural fractures in the carbonates. That's something else that somebody's going to have to think about. This is a research program in progress that I'm working on this summer. This has been known for the last 20 years at least. I think to really move forward, you got to think like an explorationist. You've got to think about the types of structures, the type of sedimentary systems to be able to predict properties where you have no data. A lot of geologic complexities that haven't been talked about yet, haven't been discussed, haven't been published on. I've kind of hit a few of them. There's a lot more. I get software from these people. Thanks, Jordan, and you guys for, I try and pay my bills on time. Surface Science Western is where I've been doing my SEM work. I've been getting funding from these guys. Enbridge has been throwing me some small projects, none of which you've seen, that help pay some bills. And the Department of Earth Sciences lets me use an office there. And thank you.